Morning or good afternoon, depending on where you're at. My name is Atarut Azizin Aminu. I'm director of the IBT / ABCUTC. Very warm welcome to more than 600 people who have registered to listen to our April 2025 monthly webinar. We are delighted to bring to you today a topic titled I-95 Bridge Collapse in Philadelphia, Accelerated Restoration of Traffic and Bridge Replacement. And we are also delighted to have with us Amelia Harris, who is a technical manager with Benesch, and that will be delivering the talk today. Now, during the registration process, we did receive a number of the questions, and we are going to try to get to them as time permitted. Paul Lies and Rick Leptic are going to be moderating the question and answer period after the presentation is finished. But if you have some additional question, please, by all means, post it on the dashboard, and as time permitted, we'll get to them, or we'll post the answer to those questions later on after the webinar is completed. Just two slides we have to share with you related to 2026 World Bridge Engineering Conference. We hope that from now you start planning to attend the conference. The conference is going to be held, this time is only 2 days, December 1st and December 2nd, 2026. It's going to be in Miami, Florida. We're going to go back to the previous hotel, Hyatt Regency Hotel. And the conference is sponsored by the U.S. Department of Transportation through our University Transportation Center. Just a couple of things. Hopefully next monthly webinar will give you the link on how to submit the abstract. The call for abstract is going to be open fairly soon. In 2026, we're going to emphasize, the title is the 2026 World Bridge Engineering Conference with emphasis on innovative bridge technologies and ABC. The conference is co-sponsored by more than 30 state Department of Transportation. The conference is going to include awards program in different categories. We are going to share with you more information, more detailed information. There will be opportunities to exhibit at the conference. We will have several keynote talks the first day, and also there's going to be opportunity, of course, based on the abstract and invited speakers to have a podium presentation. So at this point, I'm going to turn it to Kathy Kroll, who is going to share with you some additional news related to the bridge engineering. Kathy?
My name is Kathy Kroll. I'm the co-director of technology transfer for the IBT ABCUTC. I'd like to welcome you all for joining us today for the 169th webinar in our monthly webinar series. Before we get started with the feature presentation, I'd like to share some announcements with you. First, the American Composites Manufacturing Association is hosting the Design Using Pultrusion Technology Conference in Chicago, Illinois from May 6th through the 8th. See the link on the screen for further information. Next, the AASHTO Committee on Bridges and Structures will be holding their annual conference in Dallas, Texas from June 1st through June 5th. Registration is open. Information can be found at the link on the screen. Next, the Engineers Society of Western Pennsylvania is presenting the International Bridge Conference, the IBC, in Pittsburgh, Pennsylvania from July 14th through the 16th. More information is at the link on the screen. Looking a little further out, PCI, the Precast Prestressed Concrete Institute, will be hosting the 2025 PCI Committee Days Conference from September 16th through the 20th in Chicago, Illinois. Registration opens May 1st. Next, the AISC NSBA will be presenting the Steel Days 2025. This is a nationwide event that will be held October 20th through the 24th. In this event, it offers steel enthusiasts, both young and not so young, an opportunity to learn about careers in the steel industry. Lastly, For industry announcements, ASB, the American Segmental Bridge Institute, will be holding their 37th annual convention in Bellevue, Washington, October 27th through the 29th. See the links for additional information. Now for a few of our own IBT ABC UTC events. Our next monthly webinar will be on Thursday, May 15th from 1 to 2:15 Eastern. The feature presentation will be on FRP tub girder bridges in Maine. As many of you know, the fiber reinforced polymer industry has been making some great strides in offering non-corrosive transportation solutions, particularly related to reinforcing and coatings. The industry has now jumped to offering tub girders. This presentation will show how the Maine DOT is taking advantage of this innovative technology. Please mark your calendars and join us for this interesting presentation. The last announcement is our next quarterly research seminar is scheduled for April 25th. That is next Friday from 1 to 2:15 Eastern. The featured presentation will be on transformative bridge asset management using an integrated graph network, RNN approach. This seminar will be presented by our partners at the University of Georgia, and it will include information about the UTC's efforts to advance the next generation of bridge asset management systems. Please join us on next Friday. Before we dive into our featured presentation, I'd like to go through a few housekeeping items. As many of you know, these webinars are recorded and posted on the IBT ABC UTC's website in the section titled Monthly Webinar Archives. So you can access this and all previous webinars for future learning and to share with interested colleagues. I'd also like to point out that the PDF version of today's presentation is provided in the Go-To dashboard on the right side of your screen. You can download these PDFs during the training session. They will also be posted in the archives. Lastly, this presentation will be followed by approximately 15 minutes of question and answer. Please enter any questions you have in the question box in the Go-To dashboard. With that, we will begin our featured presentation. We welcome Dr. Amelia Harris, who is a technical manager at Benesch's Pittsburgh, Pennsylvania office. Welcome, Amelia.
Thank you. Can you hear me all right?
Yes.
And we're looking at the slides with my laser pointer? Awesome.
Perfect.
Great. Well, thank you so much for having me here today. Today, I'm just going to tell everyone the story of the I-95 bridge collapse that occurred in Philadelphia, Pennsylvania, not Pittsburgh, where I am. And I'm just going to walk you through what happened and the process of rebuilding. So today I'm going to cover a lot of different topics on this. So I have a quick outline so you know where we're going. First, I'll start by covering the incident and site history. We'll talk about evaluating damage, actually in two parts, but I'll start with part one on the superstructure. Then we'll move into talking about how the project team developed a solution, talk about the temporary roadway, go back a little bit to evaluating damage components, and then move on to the permanent bridge replacement, and then finally end with a summary with some nice construction photos and a few videos sprinkled throughout. So what happened? Many of you probably already have heard about this incident, but I'll cover it if you didn't. So on Sunday, June 11th, 2023 at 6:17 in the morning, a tanker truck carrying 8,500 gallons of gasoline was traveling northbound on Interstate 95 in Philadelphia, Pennsylvania. The tanker truck exited 95 at the Cottman Avenue interchange, and as it came around the exit ramp, it crashed into the abutment of this bridge, which you can see in the photo on the bottom, and caught on fire. The resulting fire was smoky, hot, and intense. Traffic on northbound 95 was quickly stopped, which is on this part of the slide, and a short time later, traffic on southbound was also stopped. Within about 30 minutes of the accident, the northbound structure collapsed, which you can see on this photo. Unfortunately, the driver of the tanker truck was killed in this accident, and fortunately, no additional lives were lost, given how heavily this section of 95 is traveled and how quickly the structure collapsed. So this section of 95 sees about 160,000 vehicles per day. Each bound of 95 is carried by a single span steel plate girder with a composite concrete deck. This structure and roadway is owned by PennDOT District 6, and they quickly found themselves in the position of having an interstate, a very heavily traveled interstate, close for the foreseeable future. So a little bit of context on Interstate 95 if you aren't familiar with this area of the country. I-95 is a north-south interstate that is about 1,900 miles long. It runs from Miami, Florida, all the way to the US-Canada border in Maine. It carries a lot of commercial traffic, about 8 to 9% of the traffic, and it's an important part of transportation along the East Coast. So with that, we'll kind of zoom in onto the state of Pennsylvania. Philadelphia is in the southeast corner of the state where the accident happened. And we can actually zoom in a little bit further. This map highlights the city limits of Philadelphia, and the accident sign is showed here in purple. And you can see that this accident occurred in the city limits in a heavily traveled, urban, and congested area. So this particular interchange, the reason that Benesch got involved with this was because we've actually been working at this site for over a decade. PennDOT District 6 has a large project initiative called 95 Revive, which is rebuilding 8 miles and many interchanges along 95 in Philadelphia. It's broken into about 5 different projects, and one of those projects is the Cottman Princeton interchange, known as CPR, and Benesch is the prime consultant on that project. CPR covers interchange improvements and reconstruction of 1.4 miles of Interstate 95. It was broken down into 5 different contracts. The most important contract for this group to know is CP2. So in CP2, that bridge that you saw collapsed a few slides ago, that contract reconstructed and widened that bridge. It was designed in 2010 and constructed over a few seasons from 2014 to 2016. So it was a relatively young bridge, which did influence some of the ideas and the direction that the project team took. Another thing to note is that most of these contracts were complete at the time of the accident. The CP3 contract was ongoing, so you may see construction activities in some of these photos that are separate from the accident. The total cost of this whole project was $340 million. So here's a good before and after shot. The photo on the left shows a nice completed, newly reconstructed interchange, and this is from 2020. And on the right, we have about 3 years later, the collapsed northbound structure a few hours after the accident had occurred. One thing to note in this picture is this highlighted area in orange. This is the last contract, the CP3 contract I mentioned. So these activities were going on at the site, but again, separate from the accident and the construction related to that. So what does a bridge look like after a tanker truck fire happens underneath it? And the answer is it's not good. So on the same day as the accident, an emergency bridge inspection took place on the still standing southbound structure. This was a visual and hands-on inspection, and the group that went out to inspect found that the heavy soot staining on the bridge, which you can get a feel for in this photo, it almost looks like a black and white photo because everything has so much soot on it. But this heavy staining really limited the team's ability to complete their visual inspection. They could not inspect connections for displacement-induced cracking. The fire department actually tried to hose off this bridge an additional time once the fire was out, but they really could not get any of that staining to come off the bridge. So this slide has some more photos from the bridge inspection. The photo on the left here, we're actually looking at the girder. It's a steel plate girder, bottom flange, top flange web. And these girders exhibited significant web distortion. Closest to the fire, this web distortion was about 2.5 inches for a web that's 43 inches deep. The photo up here on the right shows cross-frame distortion compared to a level. And then finally, there was significant bottom flange, lateral, and vertical distortion. There were also beams that were not fully bearing on their neoprene bearing pads. So it quickly became clear from this inspection that the southbound bridge could not be salvaged in any permanent or temporary form. So it was decided the same day as the accident to demolish the southbound bridge and start generating ideas to reopen both the northbound and the southbound section. Another interesting finding from the southbound bridge inspections comes from social media. This day and age, everyone has their phone on them and takes pictures and videos in all parts of their life. So as the southbound traffic was still running over the bridge and the little bit of a delay it took to get it closed, people were taking videos as they drove across the bridge. If you ever watch any of those videos, you can see a significant dip as the vehicle travels over the bridge, like a sag in the bridge. So this is a screen grab from one of those videos, and just doing some real rough proportioning based on dimensions of the median, there is a sag in the bridge during the fire on the order of 9 inches. However, when the inspection team came back, during their inspection, once the fire was out, there was no sag noted. The team actually went and measured vertical clearance, compared it to the previous inspection report, and saw no noticeable difference. However, the bridge was under a great deal of distress. This is a picture of the median barrier of the southbound bridge after the fire, and you can see significant crushing and cracking and spalling of concrete. We can even see this mat of green epoxy-coated rebar. So that barrier during the sag was obviously under a lot of stress. So once it became clear that the southbound bridge would be closed, the project team started putting together ideas. The project team consisted of PennDOT, District 6, which owns the bridge, a contractor, which was Buckley and Company, and a designer, which was Benesch. So I'm going to give you a little background on this project site to give you some context about the project solutions. So as I mentioned, it is 2 structures, one carrying northbound 95 and one carrying southbound. Each bridge consists of 8 steel plate girders, 16 total girders with a composite concrete deck. The bridge is about 103 feet long and has a healthy skew with it, 34 degrees if you use the AASHTO definition, 56 degrees if you use the PennDOT definition. Now, Interstate 95 here is actually curved. It's running along a 3,000-foot radius here. The bridge itself, the beams are not curved, they're straight, and it just has a varying overhang to accommodate that geometry. However, because of that curvature, the cross slopes of the bridge deck are super elevated, and the geometry between the 2 different gutter lines on the inside of the bridge actually differs. This doesn't matter when the bridges are separate, which they are in their sort of permanent final condition. However, when we started to bring that geometry together for a temporary roadway, that kind of difference actually mattered, and I'll cover that in a few slides. The out-to-out width of these bridges is about 75 feet. And an important thing to note on this plan view is these blue lines. These are actually sewers running underneath this ramp that leads to Cottman Avenue. These are Philadelphia Water Department sewers, and they drain significant portions of Philadelphia during rain events. The Delaware River is sort of south or sort of down from us in this plan view. So those sewers were in place, and it was important not to overload them as we started developing this temporary roadway idea. So how did the project team develop a solution? The goal was clear: restore 95 to its full capacity. And it was clear that the southbound bridge had to be demolished. And it was the goal was to get to a permanent bridge solution, which in Pennsylvania means a structure that has a 100-year service life. So one of the first ideas that came about was just rebuilding the structure as quickly as possible. As I mentioned, this structure was designed in 2010 and constructed a few years later, so it was relatively new. We as the designers still had the shop drawings for that 2010 design work. So someone on the project team reached out to a local steel fabricator, which is High Steel, and asked them, if we provide you the shop drawings today or tomorrow, how fast can you fabricate these beams and have them on site? So High Steel looked at that and said about 8 to 10 weeks. That is a really quick turnaround for steel fabrication. However, that would be getting the beams to the site. They would still need to be erected. You would still need to pour a deck and a barrier and do the concrete repair work and replace the approach slabs and weave everything together with the interstate. So that this timeline was still looking like 3 to 5 months. So this full rebuild could be achieved in 3 to 5 months, which is a really fast timeline. However, having that interstate closed for that long felt like too much of an impact to Philadelphia and travel along the East Coast. So the project team started looking at other ideas. And this is where the idea of a temporary roadway came in. Could something be constructed quickly, say in a matter of weeks, to restore some kind of capacity at the site to get traffic moving, with the idea that the permanent bridge would then be built sort of in stages around it? One issue with the temporary solution is that anywhere you build something temporary, you are building something that's in the way of the permanent bridge. So staging became very important in this in the temporary roadway and the permanent bridge stages. I-95 carries, in its existing condition, carries 4 lanes in each direction, 12-foot lanes. It has a full 12-foot inside and outside shoulder. And the project team examined plans, measured at the site, and really carefully developed staging limits for a 2-stage bridge construction that worked by a matter of inches. And in these stages, the plan was to build 3 11-foot lanes in each direction. So the solution, a little more information on the slide, involved demolishing the existing bridge and constructing a temporary roadway to open Interstate 95 at 75% capacity. So from the start of demo to the opening of the roadway was 12 days, originally estimated on the order of weeks, but the contractor was able to deliver it very quickly. This came at a cost of about $5 million for both of these projects. The demolition was completed by one contractor with a direct contract with PennDOT. Design work related to the temporary roadway was completed by Benesch that was contracted with PennDOT, and then the contractor, a separate one, which was Buckley, constructed it in 12 days, also contracted with PennDOT. Once that was complete, work moved to the permanent bridge replacement. That looked like updating the steel design first, because we had the opportunity and a little bit of time to do it, ordering and fabricating the steel, still working on that very accelerated timeline of delivering in 8 to 10 weeks, constructing stage 1, which took about 5 months to move through those steps, and then finishing construction of stage 2, which took just under a year. The work related to the permanent bridge cost about $18 million and was delivered with a design build contract for efficiency to move through the design quickly. So a little bit more about the temporary roadway solution with some graphics. So the idea was to start to build a temporary roadway in the middle of the section of 95. The idea was just to use retaining walls, fill, and build a roadway on top of it so traffic could use it. As you see in stage 1, traffic is using the temporary roadway, 3 lanes in each direction, and stage 1 of the bridge construction starts. Once stage 1 is complete, traffic is moved to the outside, again, 3 lanes in each direction, and stage 2 construction starts. And then once stage 2 is done, the site can be fully restored back to 4 lanes in each direction. Now, if you were paying attention, I told you that the out-to-out of each bound was about 75 feet. So if you start adding up some numbers, we know on one bound, we're gonna have 3 11-foot lanes, about 66 feet here, or sorry, 33 feet. We know in the next stage, which is separate, we're going to have another set of 3-foot lanes. So we're up to 66 feet of lanes, plus some room for barriers, plus a little bit of room to work to actually have space between the stages. And you can see how we get very close to that 75-foot out to out and how these staging limits really worked by a matter of inches. So now I'm going to talk a little bit more about some of these components of the temporary roadway. So here's a cross-section from our design plans. You can see 11-foot lanes on top and another set for the opposite bound. The temporary roadway consisted of leveling out the sort of area on Cottman Avenue and using a combination of steel wire walls to act as retaining walls and ultra lightweight fill to act as the fill between the walls. There are geogrid straps that extend into the lightweight fill for additional capacity. The wall extends up until we get to a reasonable elevation to put down a roadway subbase and then a typical asphalt roadway. The roadway is contained by a special outside and an inside barrier, which I'll get to in the next few slides. So the ultra lightweight fill is actually ultra lightweight foam glass aggregate. And this fill was selected to minimize loading on those sewers underneath Cottman Avenue. This is an interesting product. Typical fill might run between 120 to 150 pounds per cubic foot. This fill is very light, 20 pounds per cubic foot. Feels like a pumice stone. It has a sort of a high friction angle at 40 degrees. For this project, we used 8,000 cubic yards, and this was produced from 8 million recycled glass bottles. So there is a nice sustainability component to this kind of fill. It's very lightweight. It can be shipped by truck or even plane. It's non-toxic, non-flammable, non-porous, and insulated. And like every component of the temporary roadway, it was available for very quick delivery to the site. This particular product is made in Pennsylvania, and the fabricator actually has a couple other plants throughout the United States. This is also a product that the designer and the contractor and PennDOT have experience using in nearby and adjacent sites. So as you can see in the photo here, there is a construction worker using a hand compaction tool to compact this material. One unique thing about this is that you can't use traditional rolling equipment to compact the fill, or else it will actually start to crush it. It needs to be compacted with hand tools, and once it is and locked into its matrix, it's very capable of managing vehicular loads. So the next component is welded wire form walls that were filled with a lightweight fill. You can kind of see they look a little bit like baskets. You can see sort of the different levels of these walls, and it's sort of a grid and just is built up to the appropriate height. And the fill was placed with a lot of these kinds of machine work to use sort of ramps and hoses to get it where it needed to be on the roadway. And again, those walls are about 22 feet high. So moving up to the roadway, the outside barriers that were used were a unique product. These are precast barriers called Gravix barriers. They are basically little moment slabs. It's an L shape, and the bottom of the moment slab is loaded by a typical roadway subbase 2A, not the ultra lightweight fill. And once it's loaded, it provides some capacity for the barrier to resist impact from vehicles. This barrier has actually been crash tested and has a MASH TL4 rating. These units come in a rectangular footprint and plan, and since we have a skewed bridge site, we actually had to do some additional cutouts at these ends of the bridges, or as you moved into the roadway. So additional approach slab, diaphragm, and back wall areas were cut out to slot these rectangular footprints into the skewed site. Another thing to note is these barriers are meant to kind of sit on MSE walls, and it has this nice tab that sticks down to make like a nice appearance. We didn't need this tab. It's for aesthetics, not for structural any structural capacity. So this was removed so that the wall and the barrier could be as close to flush, because again, our staging limits were very tight. The median barrier was also unique. It is a typical embedded median barrier. However, I mentioned the existing, due to the curvature of 95, the existing roadway and the cross slopes of the bridge and the roadway needed to be super elevated. As you bring that geometry together in the median, the gutter lines are separated by about 4.75 inches. So we needed to put a bifurcated median barrier into this roadway. These types of bifurcations aren't the kind of thing that are just sitting around. So this barrier was actually fabricated for this project. So the contractor reached out to the fabricator who made the median barriers in this project during the original construction from 2014 to 2016. That fabricator had two forms that were available that they could modify. They did so, and they basically cast these barriers for 5 days straight, 24 hours a day, including a weekend, so they could be delivered just in time for construction at the site. They were shipped with a strength of 3,000 PSI, and the fabricator was breaking cores regularly to make sure they knew exactly when they could pull that form off. And they have a 28-day strength of 4,500 PSI. So from rendering to reality, one thing I haven't mentioned yet, and I think is obvious with this project, but this project had a lot of attention locally, nationally, even maybe internationally. It was a big impact to a major city on the East Coast, and there were press conferences. There was a live stream camera that was constantly running to show construction activities at the site. There was a PennDOT website set up to provide regular updates to the public. So as this temporary roadway idea and solution came into the place, we created a rendering of what the temporary roadway would look like, which is on the slide on the left. This was created 4 days after the accident, and it was posted to a PennDOT website and put up on poster boards so that the traveling public could understand what was going on here and what this temporary roadway would look like, and if they were going, because it was important for them to feel comfortable using this. So this was our rendering a few days after the accident, and then 12 days later, this is a picture from opening day, just a few hours before traffic was put on the structure. And I think we got pretty close with our rendering. So you can see in this picture on the right, the black asphalt temporary roadway, some of these rectangular cutouts at the corners where these barriers were slotted in. And if you stare at it, you can see there's just enough room for 3 lanes on each side, and you can probably imagine how there's just enough room to build another 3 lanes and the permanent bridge outside of it. Obviously from this photo, the ramp that leads to Cottman Avenue was closed while the temporary roadway was on it. And it was actually closed through the duration of construction because there was a lot of repair work that had to be done there, and it was an important area for contractor access and staging. So I have a video just to show you some highlights from the temporary roadway construction. So we're starting back on the day of the accident with the collapsed northbound bridge. And this site, those shots of Interstate 95 being completely empty are sort of jarring for me. It should be full of traffic and people trying to get where they want to go, but it was completely closed. We're moving into demolition of the northbound and the southbound structures and cleanup of the road below to prepare it for the temporary roadway. And then we're moving into construction of the temporary roadway. You can see the lightweight fill being placed between the walls. And it's clear from this shot, like this is a night shot. Work went on this site 24 hours a day to get this open as quickly as possible. We're moving up to the roadway height. And then we jump forward to opening day. Right before it was open to traffic, this traffic you see on the left side is actually detour traffic. And then here we have the first set of traffic moving across the bridge in those 3 lanes. And a short time later, that other side was open. So moving forward, the next part about evaluating damage, we talked about the southbound superstructure earlier, but there was damage to the substructure and even below the roadway. So this is a shot of the abutment near where the truck crashed and ignited. So this abutment looks black. You can see the amount of rebar exposed. There was a significant amount of spalling due to the fire. This abutment in its original form had 1.5 inches of architectural treatment plus 2 inches of cover before that first mat of rebar. So that fire was so intense that it spalled out several inches, maybe even up to 8 or 9 inches of concrete from the existing face of the abutment wall. So to evaluate this, the project, this abutment is actually just a cantilevered abutment, and it has a battered back wall. So it's actually over 4 feet thick at the base. So just from some evaluation with the contractor and the design team, everyone felt that the abutment probably could be repaired, meaning removing the damaged concrete, replacing any rebar, and then recasting new concrete to restore it. But it was important to evaluate what was actually going on there. So the project team hired a company to come out and take concrete cores all over these abutments. So this plan view shows sort of the rough idea of how the cores were taken, 12 cores more near the location of the crash and fire, but also catching every abutment to get some information. So those cores were taken to a lab and they were evaluated for existing microcracks that were left, and then also to assess their capacity of the concrete. As this concrete was exposed to intense heat, the water vapor in the concrete matrix tries to expand and you get spalling concrete. And as that concrete spalls, it leaves behind microcracks, which need to be removed to restore the concrete. So the lab took those cores back. They examined the concrete using microscopic, petrographic, and UV light examinations and found that it was the repair or replace steps of the concrete that was still there was on the order of 1 to 4 inches. I mentioned fire spalled out maybe 6 or up to 7 inches of concrete in some spots. So we detailed removal depths up to 9 inches from the original face. The lab also examined the samples for compressive strength, and that ranged from 4,700 PSI to 6,600 PSI, and this is well beyond what we use for design, so that was very comforting. The lab also reported an estimated temperature in the concrete of 300 to 500 degrees Fahrenheit. We do think of concrete as an insulated material, and it is, because it was likely that the actual fire itself was on the order of 1,800 degrees Fahrenheit. That estimate comes from firefighting teams who are used to responding to these kind of tanker truck fires. So it was a very kind of intense, hot situation, and the bridge and the concrete sort of show those effects. Moving down below the roadway, during the fire, some of the fuel entered the drainage system in the inlets and it actually ignited. So there was a lot of damage below ground. The picture that's up here right now is a picture of a normal concrete pipe. So to examine the pipes below ground, it's the kind of thing where you stick a little video camera down and you can walk it along these pipes to assess what's going on. So concrete pipes did okay when exposed to that fire. So this is a picture of a damaged pipe. You can start to see some of this sort of rebar mesh exposed. Some of these damaged concrete pipes were dug up and replaced, and some were actually slip lined and could be repaired just knowing they had a shorter service life. However, there were also plastic drainage pipes at this site, and those did very poorly in the fire. So this is a video shot of what used to be a plastic pipe, and it's basically melted and collapsed, and there's nothing left. So for all of these areas, they had to be dug out and have the drainage pipe replaced, which adds time and some of the work to this project. So moving forward to the bridge replacement, the permanent bridge. This is the existing southbound framing plan. It's probably exactly what you'd expect for a bridge that's skewed like this in a single span. So each bound has 8 beam lines. Beam spacing ranges from 9'9" to 9'11". Again, these are straight beams. The roadway is slightly curved, but that overhang varies to accommodate that geometry. And so we decided to rebuild these bridges in 2 stages. And it turns out if you split this framing plate in half, you get 2 4-beam systems that it can exist on their own in phases until they're fully connected. And that's exactly what we did. One thing to note, in the original construction and design and construction before this, there were stage construction joints along the top of the beam line because it was built in 3 phases instead of 2. And that's what you would typically do, put a joint on the beam line and it makes it easier. We had joints that were running along basically in between these beam lines. So we had to add in some checks in our temporary condition and just be mindful in construction of that really large overhang that actually exceeded the beam depth in some spots. It's not something you ideally do in a typical project, but it's something that we accommodated in this project because those staging limits were so important. PennDOT asked us to update the steel bridge design to current code. So that meant taking this from AASHTO LRFD 3rd edition up to 8th edition. So one thing we did was we changed the barrier height from 42 to 45 inches for the MASH barrier update. We also had to add a PennDOT design truck that had come into play in these in some of our newer design manuals. It's the P2016-13 truck, and it's very long and it's very heavy. So it's about 165 tons, and it has a varying length, 103 to 132 feet. And it turns out when you have a bridge that's 103 feet and a truck that's very heavy and also can be 103 feet, it can fully fit on the bridge, and it did end up controlling some of our design checks. We evaluate this kind of truck at the operating level, not necessarily an inventory level, but even at that lower level, it still does control. And as I mentioned before, we incorporated some differences related to that stage construction joint and that big overhang in the temporary condition. So some things we thought about during the steel design, we used a line girder analysis for the beam design, but given that skew, it kind of kicks us into that spot where we used refined analysis to check a couple things. So we used that to pull out cross-frame demands so we could use those in our design checks, check for uplift in some of those corners, pull out bearing rotations for that design, and check bottom flange lateral forces to make sure those assumptions we used on the line girder were accurate. We actually had 2 models for this effort just as tacked as a check. One was a Lucis model and one was an AASHTO BRR model. So a couple updates that came out of the steel design. One of them relates to the cross frames. So the existing cross frame is shown at the top of this slide, and it's probably exactly what you'd expect for a typical cross frame. It has WTs as the members. The WTs are welded to gusset plates. The gusset plates are bolted to the stiffener. Nothing unusual about this. So as we were working through our design checks, we found that we were having a lot of trouble finding a way to get the proposed, or like the weld that was in the existing design to work for the fatigue checks. It was really that fatigue analysis we were struggling with, and as we tried to make that weld bigger, these gusset plates got really large, and the geometry of the cross frame started looking really funny. So this is a situation where we reached out to the fabricator and asked if we could switch to a fully bolted connection. If you can't get the weld to work, just take it out of the design. The fabricator was fine with making that change and accommodated that. So if you go out and look at that bridge, you'll notice it's a fully bolted cross-frame connection. Another thing to note, this slide really summarizes the beam plate size changes. There's a lot of info on the slide. Basically, the thing to know is that the web depth, 43 inches, stayed the same, but pretty much every other plate got bigger. The top and bottom flanges got wider and they got thicker. The web increased, the web thickness increased in thickness by an 1/8 of an inch. And one change we made at the request of the fabricator related to the bottom flange. So in the original design, which is shown on top, there are 2 different thicknesses, and they're joined by a shop splice in the fabricator's shop. However, the fabricator came back to us and said, if we take out that shop splice, we can fabricate this beam a lot faster. Is that okay? And we said, yes, that's fine by us in design, and PennDOT was comfortable with that. This is the case where we made a little bit of a tweak just to accelerate fabrication. All right, so getting to some project summary photos. So here we are sort of back at the beginning of the project on June 11th, 2023. We see the collapsed northbound structure. We know the southbound bridge is going to be demolished. And moving forward a few days, about 5 days, we can see everything has been demolished, and we have this basically a gaping wide open hole in an interstate that should be seeing 160,000 vehicles per day. Moving forward, we have the completed temporary roadway. This was open on 12 days after the accident on June 23rd. Again, you can see the asphalt roadway, 3 lanes in each direction, and just enough room on the outsides of the roadway to start building the bridge. So moving forward into the summer, so now we're in August, about a couple months after the accident, traffic is using the temporary roadway. You can see here 3 lanes moving. Fortunately, in this picture, there are no significant backups happening, but I know that happens sometimes at rush hour. And we can see stage 1 of the bridge going into place. There are 4 beams on each side. You can actually see the cross frames are built in, full construction, a couple cranes on site, and a lot of different activity. Again, as I mentioned, the roadway to the ramp leading to Cottman Avenue was closed for the duration of this project. So one important thing about this stage 1, it was important to get this structure built before winter. So typically in Pennsylvania, our construction activities try to wrap up by November 1st because at that point it starts regularly being too cold to pour concrete. So we were still moving through design, construction, shop drawing review very quickly throughout that summer with the intent of getting it open in November. And we did succeed on that timeline. So the first stage of the permanent bridge replacement was completed and opened in early November. And then within a few weeks, the temporary roadway was actually demolished and removed from the site. So the one interesting thing to note is that the ultra lightweight fill from the temporary roadway was actually taken to another project in Philadelphia. It was a CAP project and reused there. So it was great to be able to reuse something from this site. So we're going to jump forward now to March of the following year. So traffic is using the temporary roadway. It's been on there since November of the previous year. And you can see construction activities going on in the center for the second stage of the bridge. 3 of the beam lines are up and more are to come. You can also see like more activity here. Like as I mentioned, a lot of that drainage system underneath the bridge was damaged, and a lot of the winter was spent kind of digging some of this out and replacing pipes. You can also, it's a little bit hard to see in this picture, but there was also work going on to repair those abutment walls in 2 different stages to make sure they were ready for the beams. And then we jump ahead to opening day. So this is actually the day after opening day, which we see the fully completed structure. We're back to 4 12-foot lanes in each direction, including 12-foot inside and outside shoulders. You can see maybe just a little bit of evidence of the 2 phases of that bridge pour and up through the approach slabs. I really like the shot of this picture because you can see traffic again using this ramp to Cottman Avenue into this area. So it was a long closure for the people of this area, and it was nice to see that like restored for them and returning that access. So I have one more video here sort of highlighting construction of the permanent bridge. So here we are, traffic is using the temporary roadway, and you can see 4 beam lines that have been erected on each side of the bridge. Again, very tight work site. You can really get a feel for why these staging limits work by inches. And now we're moving into deck pour on stage 1. We have our bid well, pumping the concrete onto the deck and getting it placed. A lot of these deck pours took place at night so the contractor could have one lane closed of the existing roadway for access. So now stage 1 of the bridge is done and we've moved on to stage 2 construction. We get these nice shots of beams being erected by the erection team. Again, working in a very tight site with traffic moving by really fast on both sides. And then on to deck pouring. Again, back to pouring these decks in phases, having the bid well out, the pumps, getting the concrete up there. And then we move to the fully constructed section, cleaning up the site. And then here we are, just showing traffic using the reconstructed section. Okay. So I added this slide just to have a little discussion here. So just some lesson learned from this project. It is kind of a wild ride working on an emergency project. And one of the most important things to think about is communication, teamwork, and collaboration. That's the first lesson learned. It's really important to communicate and work together on these projects, both within your, like, let's say within the design team at Benesch, but also working with the contractor, working with the client, which is PennDOT, working with the fabricators and the suppliers. It takes a lot of regular communication to make sure everyone understands what's going on. And it takes a lot of collaboration to come up with an idea like this and find all the pieces and make it all work together. Another lesson learned kind of relates to the contractor on this, but reach out early if in an emergency project to understand product availability. The temporary roadway, there are probably a lot of different ways to build a temporary roadway, but the way we did it on this project relates to the products that were available. We could get enough of that ultra lightweight fill. We could find the wire walls, and even some of the components on this project, maybe we're sitting in another contractor or fabricator's yard, maybe sitting there for a few months ready for a different project, but maybe this project took it and replaced it in a few months so it was still work for that contractor. It is, again, back to teamwork to find out what products are there, what can be used, and how you can put them all together to find a solution. Next lesson is understanding project priorities. In this kind of project, there were just some different, slightly different priorities compared to a traditional timeline of a project. Sometimes beam fabrication was important to accelerate. So there were a few cases where we made a few tweaks to our beam design or the plates we use to accelerate fabrication, things that we typically wouldn't do in a typical project, or we might want to be just a little bit more efficient. And there are examples of that all over, and it's important for everyone on the team to understand the priorities and then understand how that affects how each team is working. And then it goes back to communication and teamwork. And then finally, the last lesson is be flexible. There were a lot of changes and a lot of decisions and a lot of things that happened really fast, and it's important to be flexible and be able to adapt, move on, to drop an idea or do, just do what you need to do to get the project done. So those were my big takeaways, and I'm sure if you asked anyone else on the team, they'd probably find a few more depending on their experience. So my last slide is just some team acknowledgements. A project like this doesn't happen without an enormous team working together. So again, PennDOT, Pennsylvania Department of Transportation, is the owner, Buckley and Company is the contractor, and Benesch is the designer. And there are many other people that contributed. Aero Aggregates is the supplier of the ultra lightweight fill. High Steel, again, was the steel beam fabricator, which was great to work with. Faddis was the concrete supplier that made those bifurcated medium barriers by working for 5 days straight to deliver them just in time, and then many other companies and people contributing to the project. So with that, I'm at the end of my presentation and I'm ready for questions.
All right, thank you, Amelia. Very interesting project and a very unique solution actually for an emergency type project. So at this point, we are gonna turn it to Paul Lives and Rick Liptick, who are gonna be moderating the question and answer period. So if you could turn on your camera and stay with Paul and Rick, that will be great.
Okay, Amelia, really an interesting project. We have a
Thank you.
bunch of questions that have come in, and with that, we'll have some that came in beforehand, and I'll go on and get with those first, and then we'll go over to some of the ones that have come on during the presentation. We'll probably get some more while we're here. The first one I have, let's see, it says, given the ultralight weight foam glass aggregate in the I-95 restoration, what structural trade-offs had to be made?
I don't know if I'd say there were any structural trade-offs. You can use it like a typical fill. Maybe you just have to do a slightly different step in compaction and to place it, but there really weren't a lot of trade-offs.
Okay. And we did have another question on it. This one came in during your presentation about the fill. And let me see if I can find it here. It says the lightweight foam fill was used in replacing the material for the conventional fill due to maybe better installation. The lightweight thing seemed to be the real driver on it for those utilities pipes. But it says, does this mean that going forward, would it be better to use this material instead of conventional fill, given that a fire outbreak could occur randomly like this one?
I mean, the use of that fill, it really depends on the project and the needs. Like if there is a need for lightweight fill to reduce loading on something because of some kind of project constraints, it's a good option, but I would assume that typical fill is probably less expensive, so still valuable to use when you're thinking about costs.
Okay. With that, let's see. How was the team structured so quickly? You mentioned that y'all were sort of available, but you want to elaborate on that a little bit?
Well, yeah, the overall team, I mean, as the designer for this interchange, we've been working on this site for decades, more than a decade. And so we had an active contract on that site. So when the collapse actually occurred, we had a lot of on the ground information quickly. We reached out to PennDOT to just lend support, provide any documents they might need because we had access to them quickly. And it really just kind of, it does come down to relationships. I mean, PennDOT, we have a long history working with PennDOT District 6. We have a history working with that contractor. That contractor has a good relationship with PennDOT. So it just sort of felt like a team that could rely on their existing relationships and had familiarity with the site. So it was just natural to put that team together and start going within hours of the accident.
Okay. Then could you explain the process of how decisions were made for a course of action and maybe what some of the alternatives that were considered?
Yeah, you know, there are a lot of different needs in this project. It was important to try to open something quickly. It was important to build something, get something in place in a permanent condition. And so there were different, just different project needs, and every piece of the team brought together their own viewpoints and project needs. And it was just a lot of discussion and collaboration. And then just really as PennDOT, as the owner, making decisions what they thought was the best path forward. You do in these kind of situations have to at some point choose a path and move forward, knowing that you do have to make sacrifices no matter what decision you make.
Okay. And then along that line with the teams, it says, could you please elaborate on what strategies were undertaken by the design and oversight teams to expedite the review and approval process of design and construction submittals?
Yeah, that's a great question. As a designer, I can speak for on our end. We have a lot of staff in Pennsylvania. I'm sitting here in Pittsburgh talking about a project that's 5 hours away from me in Pennsylvania, still in the same state. But it was really just finding staff that was experienced and could be available. There was a lot of shuffling around of other projects to make people available for this so that anyone who was available could help out and review and do design work. So it was just kind of finding who was available and kind of making it happen.
Okay. And then were there ongoing working meetings and workshops to expedite or streamline the review and approval process by PennDOT?
Were there ongoing I mean, the reality was there were people sort of from each project team just parked at the site, like in their car, you know, most of the waking hours of the day. So that's how a lot of discussion happened, because a project manager from here and from someone else and from PennDOT was there, and they would just sit and have conversation, and then something would come in and they would talk about it. And you know, you people really sacrificed a lot in terms of their personal lives to be fully available for this. And that's sort of how things move that quickly.
Okay. And then how much feedback was requested from the contractor during the design plan phase? You had the thing where they requested that the splice be eliminated in the bottom flange. So anything more like that?
Probably, but you know, it was a lot of collaborative discussions and having the contractor share their ideas and the designer share their ideas and PennDOT, and a lot of that just happened in in-person discussions kind of on the site to keep things moving.
Okay. Few more here that came in beforehand for the presentation. What actions were taken to improve safety along the ramp to reduce the chance of future accident?
That's a good question. There was, you know, the geometry of the bridge and the geometry of the ramp stayed the same in this replacement, and there was just a, you know, PennDOT looked at the site. There was just some additional signage that was added to try to warn drivers of the, you know, sharp curve ahead, but just to try to encourage people to reduce speed and take that a little more carefully.
Okay. Let's see. The question came in on the existing steel. You did not reuse the existing steel in the job. Nope. But they would ask, or properties of, you did evaluate the concrete in the abutments in the
Correct.
steel. But it says,
yeah.
But for the structural steel, they'd ask questions about whether any testing was done on that. But if you didn't use it, that was just salvaged, I guess.
Exactly. I mean, NTSB was at the site. There's a chance that perhaps they did work. I don't know any information about that, but there is still a report coming at some point from them that might have more information.
Okay. Let me look at some other questions here. Time. We're doing good on time. What was the result of all the gas in the local environment, and how was it mitigated, and what was the cost of the cleanup? That was in the accident.
Yeah, that's a great question, and I don't know the answer to it. I'm sure there is some kind of response team that comes out for accidents like that, but I don't know the answer to that or have that information on me.
Yeah, usually in a hazmat accident, the environmental people are in charge. They'll eventually turn it back over to the DOT, and after that, it's can go forward. In rapid response bridge projects like this, how did the engineers find balance between the compressive strength requirements of the fill material and the urgency of installation time frame?
Emergency installation, I mean, as far as I know, this Aero Aggregates has a installation plan and details they suggest, and the contractor just followed those. And you know, you're going to have traffic riding on this for many months, so it was important to follow that plan, and the timeline sort of is what it is, resulting from that.
Okay. Was there any worry about settlement?
There was, you know, obviously with any fill, there's concern. One thing I didn't mention is that there was sort of a grid of sensing targets put on one of the walls of this temporary roadway, and there was a little bit of slight movements noticed during fill and when the roadway was placed, but once the roadway was on there, there was really no significant movement noted as traffic was using it for that time period.
Okay. Were prefabricated beam or deck elements modules considered for the permanent bridge structure?
I believe they were considered, but I'm not sure they could be sort of gotten to the site in a timeline that would make sense. And also sometimes those elements have sort of a wider footprint beyond the roadway, and we were really trying to make those tight staging limits work, which we could do with sort of these components that we found here.
Okay. We had a question, the final cost of replacement You mentioned some prices. You said 5 million for removal.
$5 million
right?
for the removal and the temporary road, and then
Okay.
18 million for the permanent bridge. So
Permanent bridge. Okay.
yeah.
So you covered
So
that.
somewhere on the order of $23 million.
Okay. All right. And I think we did have one question here about, was the trucking company, did they have to pay any fine?
I don't know. That is kind of a litigation matter, and that is well beyond my abilities.
Okay. That has got us till about the time that we started the question and answers. I'm going to go ahead and turn it over to Rick. We do have a few more questions that have come in. Rick, you want to pick up?
Thanks, Paul. Hi, Amelia.
Hi.
Well, and another question part of that, Paul, that I think about the fines on the truck, or on the trucking company, was there anything discovered about that, that led to it with a truck driver? And I'm assuming that's all part of the investigation type of thing and outside of the scope of your involvement in this project.
That is
so
correct.
Just to kind of clear the air there on that, right? We're not.
I would punt that to any other, investigation. I don't know what the answer is to that.
Yep. So wondering whether normal fill materials could have been used instead of the lightweight fill. That was a question.
Yeah, so there was concern about overloading those sewers beneath, and even probably the day after the accident, that Monday and Tuesday, we were actually in the office, doing design load calculations to look at what the additional weight was, maybe, and doing a little bit of analysis on some of those to evaluate what the additional loading of the ultra lightweight fill would be, and if that was a concern. And just kind of knowing that, I don't really think traditional fill was an option, just giving sort of what the goals and the comfort of the water department.
Yep. Now, I'm assuming those repairs were any of that pipe needed to be repaired even under the lightweight fill, or was those repairs done after the bridge was done or completed?
Yeah, a lot of those like drainage pipe repairs were done after the temporary roadway was removed. So it was just, that was when the timing allowed it.
Sure. Yep. Let's see. You mentioned the adequacy or the code checks on the superstructure, but there was a question here: was the abutments and the substructure checked? I know you did the concrete testing, but was there code checks on all the design? Okay.
Yeah.
One question here. So you found an issue with the some of the welding and the details that had to be changed. Is there other bridges in the corridor that are being looked at, I guess, since some of that stuff was found?
What I would say, I was like, that welding, it was probably appropriate for the code of that time period. So it's not really a flag for something wrong. It was just changes in code from 3rd to 8th edition, just led us to some different checks on it.
Sure. Let's see, temporary, or any other type of temporary deck supports required for the overhangs. I know you mentioned the wide overhang there on the staging issue. Did you have to do anything special with that?
I think we just had some heavy duty brackets, and we knew about that overhang, and we sort of incorporated that into our temporary steel design checks. Again, not something we typically do on a project, but it's the kind of problem you are able to solve and make happen on this kind of project.
So that lightweight fill, there was a question here: was there any concern about how that aggregate would perform under cyclical loading? Obviously, the traffic going over it, would it? I know you mentioned that there was, the compaction effort had to be very careful, and I guess, was there any concern about, long-term settlement? I guess it really wasn't a long-term job, so it was.
Yeah, it's a product that's been in use and it's been tested in like transportation environments. The actual supplier could probably answer that question better than I could, but I don't think there was any concern. And based on the sensing stuff we saw of just like any issue with like settlement in that short period of time. And it is a product that you can use in a permanent condition.
So when they removed that temporary roadway, that fill and the welded wire, the MSE wall and stuff, was there any special equipment used, or was that just pretty standard,
That's a good question.
excavator
I don't
and
know. I would
stuff.
assume it would just be standard equipment, just, stay in the staging limits.
Yeah, rip and tear just to get
Yep,
it out of there,
exactly.
right?
Yep.
Yeah, so, okay. And then there was also a question about cellular concrete. Was that ever considered as a lightweight fill? But that would probably be a little more difficult to take out than what you.
Probably a little bit, yeah.
So, okay, with that, I think we're pretty good. We got a little bit more time, but we're out of where the questions are kind of. I don't see too many. I don't see any new ones, so I think we've met everybody's interest at this point. And it's a really good. Amelia, it was a good presentation and really looked a nice project. So I guess we'll turn it back over to Adirad to wrap things up here. So thank you.
All right. Thank you, Greg. Thank you, Paul, and thank you, Amelia. Very interesting, very unique solution. So on that note, we are going to conclude our webinar and hope to see you with us next month. So long.